Hello everyone, in this video I'd like to combine two things. So first I want to show you my new updated setup on 6502 development. So I was mentioning that I'm writing code with pen and paper, and this is the ongoing work with the printboard function. But another update is on a printboard function itself. So the previous version of the printboard function did take 117 bytes, which was an overkill. So I had to entirely rethink the board representation. So here we have the board representation in order to make the code really shorter. And also I've been mentioning a lot that I'm currently writing 6502 assembly code on a paper using the pen. And then I do some hand assembling. I have these table to convert assembly to to the opcodes. Okay, also have some routines to work with Q1 operating system. This one is for non-serial mode with the keypad mode, but I also have this one which helps me to work in a serial mode. But since I've moved to the mobile emulator of a Q1 that I've been developing back in the day, it allows to enter opcodes within the keypad mode, but it also has the serial terminal kind of window there to be able to print using the 1EA0 function to print a character to the TTY. It's not capable of reading from the TTY, but the program that I'm developing, the Wally from the Byte magazine 1981, April by John T.K. Millen, it did assume that the user would be entering moves to play the game of Go using the keypad, and the computer will respond with the best move on a KIM display, 7-segment LED display, but it will also print the board to the TTY. So I'm trying to sort of replicate that kind of behavior. Anyway, let's get back to our board representation. So currently, I only have 30 bytes to print the board, which is definitely less than 117. So let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30. Okay? So, you remember that we have a board of 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 15 by 15. But we also have some free spaces. And these free spaces are used as off-board squares. And the previous implementation did have the very first square over in here. And off-board squares did not go like this, but they went like this instead. Okay, but that wasn't efficient because in order to print these values, the column numbers. So these are the ASCII characters encoded. So this is the ASCII character of 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the ASCII character of A, B, C, D, E, F. Same for rows. So I thought that I can essentially, instead of writing some code that would be converting these the loop from 0 to 15, then convert the integer to the ASCII character by adding either 30 if the value is from 0 to 9, or the value of 41 if the value is from A to F. But that was lots of branching, it took lots of space, lots of bytes to come up with that function. But here, essentially, I can do a single print string function. So the entire board is like a single print string function, because these are the characters. Okay, and also when it comes to representing the empty squares, 2E stands for period. 23 stands for, it's the hash symbol, it represents the black stone. So black stones here in the corners, the 3 3 sun points. for F is the uppercase letter O, which represents the white stone. So essentially, if I encode the board using the bare ASCII characters for both the values on board and for the column and the rows, which are absolutely essential because it's very important for user to see like where to put a particular stone. So the user would be seeing the board, which goes like this, so like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, etc., etc. And here is like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. And say we have like periods here, which represents the empty kind of empty squares, etc., all over the board. Let's say we have some a black stone over in here. So I'm just doing the ASCII character representation of the particular board that we have over in here. Same goes here, just don't want to spend time on this. So say user wants to place stone in here. So he can just take the coordinates. So first the y coordinate row, so 3 and 4. And he says like 34, I want to set the black stone like this. And essentially the 34 would be the exact address of this particular cell in a 0 page, because it would be like hexadecimal 300, hexadecimal 34 would be corresponding exactly to this location. So previously, when we had an offset, when the offboard squares went in here, we needed to do like we had a 0 based coordinates. Now we have like 1 based coordinates. So there is no such a thing as a 0, 0, because on a 0, 0 we have coordinate. This is the offboard, and just to make sure we use this still, we use this notation ASCII character encodings here. So essentially, we print the board as a single string. So let's quickly walk through the source code, and then I will show you my mobile emulator of Kim1, and we would enter these codes into the emulator and run it and see. We won't see something like this because I did not yet implement the initboard function, which was the topic of the next videos, hopefully. But at very least, we'll see how user can set up the square in a certain memory cell in a 0 page, which is super cool. And yeah, we would not only be setting the stones, but also probably some empty squares, just to show you how this kind of works. Anyway, so we can start with, so here is the printboard function. Interestingly, this function can be put wherever in memory. It's not tied up to a certain address, because I'm not using jumps here. Instead, I'm only using relative branching, which gives me an option to put this code into like 200 hexadecimal, 300 hexadecimal, wherever I want. So this is a really flexible approach. So we could start with initializing the X register to 0 to reset the counter. So X would be serving as a counter, transferring this value to the A register. Then if we bitwise end this with 0f, and if this is the case, then we track this kind of column. And this means that we are off board. In this case, we want to print a new line. Okay, and when we print, and also we not only print a new line because we start from this one, so we're not skipping this. Usually we would like to skip offboard squares, but since this is the print routine, we don't particularly need to skip anything because we also want to print the offboard squares, which do contain our coordinates. Okay, so in case if we encounter the very last element, so 0f in the index, in the square index, so this is like 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 0A, 0B, 0C, 0D, 0E, 0F. So it contains F. The last 4-bit is F. So this is offboard, which means that we want to print a new line and then start printing this one, so that this line is not going here, but this line starts like from the new line. So that's the idea behind this new line. So new line starts here. So say we print this. So we just printed the notation. Then we jump to the new line. So what happens there? Jump to the new line. So here is the new line. We need to preserve the value of X register because the subroutine to print the new line and carriage return alters the X register. So I'm transferring X register to A register, pushing A register to stack. Then I print the new line character, and carriage return. This is the Kimbrom routine to do this for us. Then I take back the value of A register and reinitialize the X register back because it was messed up after this routine. After this, based on the value of the X register, branch on carry clear to print character, and the print character is over in here. So in case if we didn't run out of 256 bytes that do represent our board, in this case we want to continue. Otherwise we just return. So after we print the very last new line, we just return from the subroutine. So we jump we conditionally branch to print character, which is over in here. So here I'm loading the value at the 0 page plus the offset of X. So this would be printing the value of, so this command loads to the A register this value, then this value, then this one, then this one, then this one, and up to this one. Okay, so we load the next value to the A register, then we jump to subroutine to print whatever we have in the A register. Then we jump to the subroutine to print the space, just for nice indentation. After this, we increment the X register, which essentially we loop over every next cell because it will be used here to index the 0 page with the proper counter. Okay, and in case if we did not run out of 256 bytes, in this case we just go back to our print loop and we continue this one. And on demand we do our new line character print, and then we jump back to the print character over in here. And if we are done, say we go from this one, so the X register would wrap around if the X register contains the value of FF, and then we do +1, which increment X essentially does. Then we go here. We don't want to print the board one more time, so this case 0 flag would be set because X register would be equal to 0, so we can do branch equals, which works whenever the 0 flag is set to 0. We go to print return, and print return is I put this in the wrong place essentially. So print return is here. Print return. So 60 just to return from the subroutine. So this is essentially it. Now let's try to input these codes into Q1 memory and try to play around with adding some values. Well, okay guys, so let's now try to input our opcodes into the memory. So essentially I can put this code that we just had a look at to any place other than 0 page. For now, just for the matter of demonstration, just for testing purposes, let's put this to 0 to 0, 0. Okay, and I'm going to the data mode so that now I can affect the data. Okay, and I just input the opcode. So we have A2 load the immediate value to the to the X register, and 0, 0 is the value. Okay, then transfer X to A is 8A. The next one is 29. This is compare with the immediate value of 0F, and then branch equals is F0 to 0D. Okay, and then load to accumulator the value at the 0 page plus the offset in the X register. This is the opcode B5, and 00. Okay. Now jump to subroutine to print the single character, to print whatever we have in the A register as the ASCII character, and then we want to print empty space. So these are the keyROM routines again, 1E. Then incrementing the X register. Okay. If we did not hit the FF, we want to loop back to the beginning of the loop, F0. So this is the relative offset, okay, which makes code possible. Otherwise, we want to return, so F0. And now we jump forwards 9 bytes to the return statement, like this. Okay. Now we want to preserve the X register in the stack. So we do txa, transferring X to A, which is 8A. Push to the stack 48. Then we do the subroutine to print the new line character and the carriage return. So 2F plus 1E. Okay, then we pull back the value of X register to the A register, and then we transfer it from the A register back to the X register. Okay, and now based on what we have in the X register, we want either to return or to go back to printing the next character. So branch on carry clear is 90, and we branched back to EA. Finally, we have 60, which means return from subroutine. Now let's go to addressing mode back. I need to carefully check everything because I could misclick or something. So A200, A8A, 290F, F00D, B500, 20A01E, 29E1E, E8 D0 F0, F009, 8A 48, 22F1E, 68AA, 90 EA, 60. And I hold my breath, and if I do everything properly, this should essentially now print it's not the board, but print whatever we have in the 0 page to the serial monitor. So let's go to 0300. This is where we're supposed to be calling our printboard function. Going back to data mode. Now I say 20, which is jump to subroutine, and 0002. Okay, going back to addressing mode. So we want to call the function located at 200 hexadecimal now. Okay, and I hold my breath and press go. Okay, we got some output in the our serial monitor, but we have some gibberish here. That's the reason. The reason for that is that mostly we have zeros in the 0 page. So we now start putting some values to see how nicely this is going to be working. So I go to 0000. Now let's enter the values for the column coordinates. So go into data mode, and 30 is the ASCII value for 0. Then we have 31. Then we have 32. Then we have 33, 34, 35, 36, 37, 38. We'll then create a function to do this automatically for us, but for now, 39. Now, ASCII value of the uppercase A is 41. and B is 42, 43, C, and 44, D, 45, and 46, E, and 46F. Okay, and the next one after 46 would be the first row. So the first row is 31. Okay, and then we can do 2E, 2E. I'm not going to be entering all of those, but just to enter some values for the empty square. So we should have the first line being printed now, all the coordinates, then the first row, so vertically would be 0, 1, and then 3 periods representing empty squares. So again, let's go to 0, 3, 0, 0, and I try to run my stuff again. Okay, and let's scroll a little bit. It still has the output from the previous output, but that's okay. So the new output starts with this 0, 1, 2, 3, 4, 5, etc. I'm thinking that maybe I could adjust my emulator a little bit so that it just clears the output entirely. But anyway, yeah, so we can keep entering these values manually. But yeah, let's essentially, yeah, I could do like 44, for instance, or 33. Yeah, let's just try to put some stones. It would not print all the empty squares. It would not print all the coordinates. But well, essentially, we can just skip printing all the. We can skip printing all the empty squares, but we can print all the coordinates and place a few stones. So hopefully that makes sense. Okay, let's go to 0 page back. So this is the value of 0, 0, 0, 1. No, hold a sec. 1, 0, 2, 0. So if I go to 0, 0, 2, 0, here I want to set the value of 32. Then I go to 3, 0. Yeah, skip the entire row essentially, yeah. And here, this is going to be 33. Okay. And okay, it's faster to go back to here, 0, 0, 40 and eta. So this is going to be 34, 0, 0, 5, 0. This one is going to be 35, 0, 0, 6, 0. This one is going to be 36, 0, 0, 7, 0. This one is going to be 37, 0, 0, 8, 0. This one is 38, 0, 0, 9, 9, 0. This one is 39, and then A, B, C, D, E, F left. So 0, 0, A, 0 is going to be 41. Then 0, 0, B0. I cannot set all of those because some are used for program counter and stack pointer, those used by the keyROM like EF, F0, so I would not be capable of setting those because in this debug mode, they would be overwritten by the Kim operating system when I type something on screen. Yeah. But anyway, just at least some of those to be there. So B0, so this should be 42 data, 42, 00, C0 data is going to be 43, address 00, D0, 44, 00, E0, this is the last one, E0, this would be 45. I cannot say set F0 because it's used by the operating system. It would be possible when the real program is running like within its own loop. Like if I drop back to the operating system ROM loop, I cannot set that. Oh, I can, but it's not going. Maybe it's not going to be reflected properly. So the last value here I set is 45. So it would start at E, not at F. But anyway, should be just okay. Let's go back to 0300 and try to run this again. And yeah, so we have coordinates, so 0 to F. And now we have the rows being printed. Cool, isn't it? Yeah. We still don't have the F, yeah, due to the reason I mentioned. So now, since we have the coordinates anyway, we can now try to put some stone. So let's put Blackstone at 3, 3. So it's very simple. I go to 0, 0, 3, 3. And, okay. 0, 3, 3. And the value for the Blackstone is 23. So I'm going to data mode. I do 23. This would print the hash symbol. And yeah, let's go and see 0, 3, 0, 0. Go. Go. Okay. Yeah. Yeah, I just messed up. It's not 3, 3, it's 2, 3. Why is that? This is a little bit unclear. It did print the Blackstone, but I'm not sure about the particular place where it should be. No, don't select anything. Okay, 0, 0. Oh, it's maybe 32, not 33. Nope. This is strange. So why is that happening? 33 is not set where it should be. Okay, if I just try to set this in the next one. Yeah, I messed with coordinates somehow. I'm not quite sure. I need to figure this out. I'm still debugging, yeah. Anyway, so 0, 3, 0, 0, go. Yeah, so for some unknown reason, the x coordinate or the column seems to be 0 based. Oh. Oh, hold on a sec. Does that make sense? Yeah, probably this does make sense. So I would need to adjust this by 1 when it comes to the user input. What's the reason for that? So when it comes to rows, yeah, the first row is never taken. But yeah, why is this not working with columns? I'm not quite sure. So if I want to set the 4, 3, I essentially need to set the 4, 4. So down below the Blackstone, I want to set the Whitestone. So this would be 43, 44, essentially 0, 0, 44. Say I want to print the Whitestone, so 4F address 0, 3, 0, 0. Okay, one last thing to do. I just set this one to 0 and try the next one, and setting this one to 4F. Yeah, something goes wrong with the address. I'm not sure if there is the bug in my code or what's wrong. Probably, yeah. I'm not ready to answer this question now, really. But anyway, the goal of this video is just to show you the spirit of this old school development. Yeah, now it's printed properly, but I'm not sure why is that. So maybe give some offset over the. Yeah, I don't know. I don't know really. But anyway, guys. Yeah. Hopefully next time I will get clear with what was wrong this time. And also next time there should be a function to automatically initialize the board for us, so that we could see the entire board filled with empty squares, and then we can just try playing around with setting stones, and hopefully the this coordinate system will be working appropriately. This is it from my side. Thanks for watching. I'll see you next video. Until then, and cheers.